Consider a robot with limited viewing distance exploring an unknown area. We can see its direct environment. But as it moves around, it is hard to get a complete picture of the scene. Now consider a swarm of robots. They can explore everything, and they can stay around so that we can get live updates of the full environment. How can we organize this swarm to explore an unknown area and make sure we continue to observe parts after they are discovered? Having swarms of inexpensive robots without mapping capabilities in mind, this is our idea. Initially, we only see the entrance to an unknown environment. First, we place 2 robots there. Then we send another one into the area to build a triangle of 3 robots that see each other. We continue iteratively, sending in more robots. Each of them uses the triangulation for navigation and guidance and extends it with a new triangle. In the end, everything is covered with the triangulation. We can use it to describe the geometry of the environment and as an infrastructure for navigation. Low-cost robot swarms for such an approach actually exist. James McLurkin and his team at Rice University have built such a platform.
This is the R1 mobile robot. It is specifically designed for multi-robot research. In particular, it has the sensors required to determine the bearing and orientation to neighboring robots. This is your ideal vertex on your computational geometry algorithm. Another key system on the robot is the infrared communication system. It consists of 8 transmitters located around the perimeter of the robot and 8 receivers also located around the perimeter of the robot. With the system, the robot can communicate to other neighboring robots, and because there's so many receivers and transmitters, it can figure out if this is another robot, when this one is receiving its signal, it's going to receive it on this receiver and this receiver. So it now knows the direction of the neighboring robot. Likewise, when this robot is transmitting, it's going to transmit not quite the same message on all 8 transmitters, so this one now can figure out the orientation of the neighboring robot.
For algorithms, we model the R1 as follows. Its infrared communication has a sharp circular range which we normalize to 1. So every robot can observe a unit disk around it, and it can exchange messages with every other robot in this disk. It cannot measure distances. It uses 8 transmitters and 8 receivers, so there are 16 sectors that can be distinguished. We use these sectors as approximate angular sensors. Using this model, we can formalize the problem at hand. We define the minimum relay triangulation problem as follows. Given an unlimited number of robots entering an unknown polygonal environment through a door, triangulate the environment. Minimize the number of robots. In a 2011 paper about this problem, we showed that the offline case is NP-hard but admits an approximation scheme. For the online version, no algorithm can have a better competitive factor than 6/5. We were able to develop a 3-competitive algorithm. Here's how this algorithm works. We need a robot on each of the polygon vertices and on long walls anyway, so we place these green robots first. No optimal solution can cover the walls with fewer robots. Then we fill the interior with equilateral triangles and blue robots using an arbitrarily oriented grid. In some places there might be a single robot. No optimal solution can cover the polygon with fewer robots. The green and the blue triangulations are not aligned with each other. We fill the gap between them using red triangles. We may need additional red robots in this step. By bounding the number of green, blue, and red robots, we can prove that we use at most 3 times the robots in an optimal solution. This means we have a good strategy for min-relay triangulation using our unlimited population of robots.
But I don't have an unlimited population of robots. I only have 59.
Okay, we can work with that. This changes the problem. Let us rephrase it. Given a bounded supply of robots entering an unknown environment through a door, triangulate the environment. Maximize the area covered by triangulation. This problem is called the maximum area triangulation problem. These changes do not affect the complexity of the offline version. For the online case, consider this scenario. After entering the unknown environment, we face many narrow tunnels. While exploring them, we use up our complete robot supply, but cover only a small area. If we had guessed the right corridor to enter, we would have found a big, wonderful world where we could have triangulated a huge area. This proves that no competitive algorithm is possible for max area triangulation. So, for real robots, we need a good heuristic. It must be simple enough to be executed by our robots. We start with 2 robots at the entrance connected by an edge. This edge is marked active. It indicates the front of the explored area. A new robot enters, selects the only active edge, and passes between its 2 endpoints. It tries to create a large triangle by finding a good spot for a new vertex. For that matter, it runs a finite state machine that fixes the angles at the 2 endpoints, one after the other, and stops. It then marks the 2 new edges as active and the old one as inactive. Now, active edges can recruit robots from the supply. New robots build a route through the triangulation. Within each triangle, another angle balancing scheme is used for navigation. The robots drive along the route, leave the triangulated area, and extend the triangulation. All navigation tasks can be solved using angular location information. Building a coordinate system is not required. Here we see a large swarm of R1s executing the algorithm at the Rice Multi-Robot Systems Lab. So we can get these cute fellas to execute sophisticated computational geometry algorithms. They explore, build a triangulation, and create an infrastructure for navigation and observation.